Let's roll the tape.
Hello, space fans, and welcome to Professor Britton's Wacky Universe.
All right, guys, welcome back. It's time for part two. It's time for our second half of the lecture on the sun. It's so nice to have you guys with me once again. And hopefully today's class will go off as smoothly as the first one went. One thing I'm gonna do before I get started, I'm going to hide the non-video participants because actually, I think those of you who are willing to share video with me, it really adds a lot to the class because then it can be more like a dialogue instead of just me kind of talking at an empty camera here. So let me go into my video settings and I'm going to hide non-video participants. If you are a troll, that's okay. You are free to troll the class and hide in the shadows. We will give a lecture for you too, but for those of you I can see, thanks a lot for participating. That actually helps me too, because I can figure out if you're still writing when I'm giving notes. You know, like I pick up on a lot of cues in the classroom. If I can see, hey Marcus.
Blue, please.
I can tell if you guys are ready for me to move on or not, or if you're, you know, waiting around bored. It helps to get a little bit of visual feedback. Okay. So hopefully we can have a good show today. Remember our plan. Our plan is to have a great lecture on the sun, dive into the interior of the sun and learn about its various layers. I'm hoping, if all goes correct, that the lecture will terminate with nuclear reactions inside the sun and we can have a wacky lecture on nuclear physics. And I have a slightly dangerous demo to do that involves radioactive rocks. So probably the only one it'll be dangerous for is me, since you guys are far away. I also have...
Good time to be on video chat.
And I also have those radioactive rocks.
You got some radioactive rocks?
Yeah.
Okay, do you have a Geiger counter?
I have a little dose of, I think it's a little bit extinct, but it's plutonium.
You have plutonium?
Plutonium.
Okay, if we ever get to have lecture in person again, if you have a sample of plutonium, you have to bring it in. I have a test sample of polonium. I don't have, if you do have something like that, you bring it in, we'll put it under the Geiger counter and watch the thing go click, 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 okay?
Yeah.
But I'd be surprised if you had plutonium. That's pretty amazing. I want to show you guys something else before we get started here, something that I'm hoping is going to work today. Let's do the screen share, and let's screen share the iPhone. And I will go here to mirroring Zoom Be Britain. We're now connected and I can, let's see if you guys are, oh, hold on. Something went awry. Screen mirroring, Zoom Be Britain. Okay, there we go. I see, I chose stop mirroring. Check this out, guys. Hopefully you'll be able to hear me if I walk over here, but I actually set up a, an 8-inch telescope right here in my apartment, okay? Now, attached to my telescope is a solar filter. If you guys look here, you can see I've got a solar filter attached to the telescope. And the solar filter basically blocks 1,000th of 1% of the light. And the only question I have is whether or not we'll actually be able to point at the sun. If everything goes correctly, I'll be able to show you the photosphere of the sun right here from my apartment. Now, my apartment is downtown in between a bunch of buildings. So there's a kind of Stonehenge effect going on. And I'm hoping that if the sun goes right between those two buildings, which it usually does because they face south, at some point in our lecture, the sun's gonna go right between those two buildings and I'll be able to point the telescope to the sun, put the eyepiece up, put the iPhone up to the eyepiece, and you guys will be able to look at the disk of the sun. That'd be a pretty great demo. So let's hope that works. Okay. Let's Let's see here. I want to go to speaker view for our recording, and I want to lock myself. Okay, good. Let's think about where we ended up last time. Last time we ended up talking about the outer layers of the sun a little bit. We talked about magnetic fields. We talked about the composition of the sun. We talked about some of its dimensions. And today we're going to start with a really important lesson called hydrostatic equilibrium.
Yep.
Can you hear me, Riker?
Yeah, no, that was what I was going to say. Next time, hydrostatic equilibrium. That was where you were on to start us this week. I made notes.
Somehow I remember all that. So let's go to our slideshow real quick. Let's see here. I'm going to bounce around between the share screen view. I got to get this stupid, hold on a sec, guys. I've got to increase my window so it doesn't interfere with the taskbar. There we go. Okay. This way I'm almost, but not quite full screen. All right, so I'm going to share screen, and we're going to go to our lecture on the sun. And I'm going to jump ahead to a slide for hydrostatic equilibrium, and that's slide 18. So if you follow along with us at home, if you downloaded the slides, this is my sort of standard slide about hydrostatic equilibrium. And I like you guys to sort of see the picture here before we begin, okay? So this is the picture you want to have in mind. Let me stop sharing for a moment. Hydrostatic equilibrium is an important concept, not only for the sun, but also for other stars that we are going to study in this class. And it's sort of like the answer to the question, why does the sun, which is a ball of gas, what causes it to hold its size and shape? And let's think about this. If you have a bottle of perfume and you open the stopper on the perfume, you can actually smell molecules of gas as they evaporate and travel around the room. If you watch a science fiction movie and they space someone, if they open up the airlock, all of the gas rushes out of the spaceship into space. So if the sun is a big ball of gas in space, why doesn't all the gas just disperse and blow away? Why should a ball of gas stay intact in space? You guys know the answer to that question?
Well, if we can go back to the slide, I can tell you.
Is it its own gravity pulls it?
That's right. And that's the idea behind hydrostatic equilibrium. So let's take a couple of notes on that, okay? So this is an important concept in stellar astronomy. Hydrostatic equilibrium.
Oh, shit. What did I do with my pen? There it is. Yay.
Can you guys read this okay? Get
Yep.
a little closer. All right. Hydrostatic equilibrium is defined this way. It is a balance of forces, and I do mean forces in newtons, between gravity pulling in and something called thermal pressure pushing out. And although this starts off sounding really simplistic and not super sophisticated, actually it turns out that there's a little bit more going on underneath the hood here than you might think. So remember, this answers the question, why does the sun, which is a ball of gas, keep a fixed radius? And let's think about this. There's going to be two reasons why the sun seems to have such a fixed radius. Hydrostatic equilibrium is one part of that equation. Let me go ahead and share my screen with you again, and let me share this slideshow. And I want to go back just a picture here to this kind of cool photo that I found on the internet. Here's a person who's framed themselves such that it looks like they're holding the sun as an illuminated orb in their hands. We can see the sun, the disk of the sun, with our naked eyes on the sky. Of course, it's somewhat dangerous to look directly at the sun, as our president has demonstrated in front of television cameras. Usually the safe way to do this is with a pair of Eclipse Shades. And I happen to have a whole bunch of them here at my house. So here you can see I got a couple of different pairs of Eclipse Shades. I have a bunch of these floating around. And Eclipse Shades are fun because they reduce the intensity of the light from the sun so that you can kind of look directly at it. Now, when you put these things on, you can't see much of much, but you can look up at the sun and just stare at it and see its perfectly formed disk. What's the angular size of the sun in our sky again, class? I just want to make sure you remember things. What's the angular size of the sun? Oh, geez.
Half a degree.
Yeah. Thank you. Half a degree. Thank you, Michael.
No problem. Got your back.
Thanks. If the sun did not maintain a fixed radius, we would see it on our sky. Think about how weird that would be to watch the sun grow and shrink. Believe it or not, there are a class of stars that we will discover later, known as variable stars, that do not maintain hydrostatic equilibrium, and they do not maintain a fixed radius or size and shape. And although we cannot resolve the disks of other stars in our sky, you can actually look at these stars with your naked eye, and you can watch them grow and shrink. Oh, I'm sorry, not grow and shrink. You can watch their brightnesses change. So you can see the intensity of the star, usually measured in magnitudes, growing and increasing. One famous example of a binary star, which is not in hydrostatic equilibrium, let me get my other slideshow up here, is the North Star Polaris. And I have a slide on Polaris to remind you about that again. Just give me a second here where I fiddle through it. Where's Polaris? Where's Polaris? Here we go. Here we go. Slide 80. That's why it took me a little bit of time there. Let me find my Zoom again. Share screen, introduction, boom. And now let me go to function F5, slide 80. Boom. So you guys remember that the North Star, Polaris, is the tail of the Little Dipper, or Ursa Minor, the little bear. And Polaris varies from a second rank brightness star to a third rank brightness star over the course of a month, or about 30 days. So this is a star which, if we lived on a planet in orbit around this so-called sun, we would actually see the size of Polaris grow and shrink on our sky over the course of a month. And probably the energy or the intensity of light that it's putting out varies as well. So a planet would have a difficult time keeping long-term temperature stability because this star's radius would be growing and shrinking at a significant fraction. The only reason I'm telling you all of this is to let you know that not all stars behave like our sun. Not all stars maintain hydrostatic equilibrium and maintain a fixed radius. But this turns out to be actually very beneficial for the development of life on Earth. We want a steady sun that keeps a fixed radius, that maintains a fixed energy output, because long-term climate stability is helpful for life to develop on Earth. Okay, now we have to have a little kids break so we can talk about this concept here, thermal pressure. Let's think about thermal pressure. The word thermal suggests it's related to temperature, and that's a discussion that we had sometime before our spring break and before the coronavirus broke everything all hell loose on us. What's our fundamental definition of temperature? Let's look at an ideal gas together and think about what that all means. So let's go back to our animation of an ideal gas, and let's imagine that these particles here in slide 22 are the gas atoms that are bopping around inside the sphere of the sun. Class, what's the composition of the sun again? I gotta make sure that y'all remember stuff.
Hydrogen, helium.
Hydrogen and helium, and then 2% metals.
Okay, awesome. And what's the rough ratio of hydrogen to helium?
Hold on. I have those notes.
Just, oh yes, and Petrabel or?
It's 70% hydrogen, 28% helium.
Good. So I'm thinking, Ramos, that's like 3/4 hydrogen, 1/4 helium, right?
Yeah.
And that
Basically.
means if you guys can see my animation up here on the board, the blue pellets are kind of like the hydrogen atoms, and the red pellets are kind of like the helium atoms, right?
Yeah.
Now, gravity is being supported. Like for instance, if there wasn't thermal pressure inside the sun, gravity would continue to squeeze this collapsing ball of gas until it turned into a black hole. But at some point, the sun, the gas particles in the sun kind of put their back up and offer some resistance to gravity. So thermal pressure involves a relationship between a concept of pressure and temperature. I want to start off by asking you guys if you remember what our fundamental definition of temperature is. How do we define temperature?
Measures, right? I think.
Anyone?
I think.
Average kinetic energy of a system of particles in a gas, liquid, solid, or plasma.
Okay, good. So let's talk about thermal pressure. We first have to remind ourselves, what is temperature? And temperature is basically like the kinetic, all right, the average kinetic energy of the gas, right? And because I remember that kinetic energy is 1/2 mv², there is a useful lie associated with temperature that's probably better for you guys to think about. The mass of hydrogen and helium stay relatively constant, so we can define temperature in this way. Here's a useful lie. That
Professor, can you enlarge the screen?
Like the speed of the
Double click on his image and it should switch.
Okay, thanks.
I'm sorry. Oh, did you have a comment, Riker, or a suggestion?
No, somebody was asking if you could enlarge your screen. So I said double click on the image of you and it should enlarge it to full screen.
No, but you guys have a point. Sometimes I forget to put it back into locked speaker mode, and that's essential for the notes. So are you guys able to read this right now? Ramos, can you see this?
Yeah.
Yeah, now I can.
Yeah, I can see that.
Yeah.
All right, cool. Well, looking at this on screen makes me realize how slanted all my writing is. It doesn't look like that in person, but it looks extremely slanted on the screen. Okay, so a useful lie is that temperature is like the heat of the particle. Sure. So now we have to talk about what pressure is, so that we can understand this concept a little bit better. I don't suppose anyone's taken a chemistry or physics class and knows how we define pressure. Michael, maybe you remember from Astronomy 1010, that seems like something I would have talked about.
You did, but I can't access those memories. I'm sorry.
Anakin, do you remember how we define pressure?
Force per area.
Force per unit area. Way to go. Okay, as usual for the win, pressure is defined as a force per unit area. Now, that's a little bit of an abstract definition, and we should try to explain a little bit more carefully what we mean about this. Usually the force is the force delivered by the gas atoms as they slam into the walls of a container like a balloon, okay? So if the gas particles are like this, and you have some wall or some rubber membrane, like the membrane of a balloon or the membrane of a wall like this, it's the force of the gas atoms colliding with the wall and slamming off there. Usually when they draw a little physics picture here, they have some wall. It could be the stretched membrane of a balloon. We have a gas particle traveling with some kinetic energy, and when it strikes the walls of the container, it's going to bounce off and deliver a little bit of force divided by the area of this wall that it's kind of colliding with here, okay? Let's think about the units of pressure. What are the MKS units of force, students?
Newton.
Newtons. Thank you, Morgan. So the units are, by the way, sometimes in physics classes, people use hard brackets to say we're talking about units now. We're not talking about variables in an equation. So our MKS units of force are newtons. What would the MKS units of area be?
Meters.
Area is length times width, right? L squared.
It would be in meters.
Right, but meters is a measure of length, so area
Meters.
would be.
Meters squared.
That's right. So it's newtons per square meter. These are the MKS units of pressure. Let's just do a little jam on that really quick here. Okay, so so for units of pressure, in the MKS system, we define a Newton per meter squared as a Pascal. 1 Pascal is defined as 1 Newton per meter squared. Now, as a reference number that I think is somewhat helpful, air pressure at sea level, which we are at roughly in Rhode Island, air pressure at sea level is about 100 kilopascals, which you guys know is 100,000 Pascal.
Is there like a visual way you could represent pascals, or like nah?
Is there a way to represent pascals?
Like visually, is there like a size or something, or is that just like a feeling because of like it's a force or like a pressure, or is that like?
No. So let me help. I think I might be able to provide some help there. By the way, who was talking to me? I just couldn't see you.
It's Raph.
Oh, hey, Raph. What's up, buddy? Okay, Raph.
What's wrong with your nose?
I had a bloody nose. It's like the shift in the atmospheric pressure and all that. You know how it goes.
The newtons per meter squared are going right to your brain, kid. They're going right to your brain. Okay. All right. So hold on. That's a reasonable thing to ask, Raph. And it turns out that I do have a sort of goofy slide that might help with that. This is how you might see it displayed in a sort of physics textbook, function F520. You know, the pistons that drive your car forward, a piston is like a cylinder with a movable disc inside of it, and gas can be compressed and you can change the pressure. And you can literally, in a movable piston, actually place a mass, some kind of mass in kilograms, like a 1 kilogram test mass, on top of a movable piston and get the piston to come into hydrostatic equilibrium, where the gravity of the 1 kilogram mass is balanced by the pressure of the gas particles. Now they're slamming into the walls of the container, but the cylinder doesn't move, but the piston can. Notice in the second picture, they've increased the quantity of their test mass, and this mass, which looks to be about double the original mass, is capable of compressing this piston to about half its former height. And that means that the gas pressure is going to go up there. So you can see it's gone up. Now, there's a couple of different units that people use for pressure, and I wanted to talk about that. How about our imperial system that we use when we fill up tires at the gas station? What are the imperial units of pressure? You guys know?
I don't know.
Well, they would use pounds and inches.
That's right, and that's what's called PSI in your air tires, right?
Oh, PSI.
PSI is pounds per square inch. Very good, Riker. Now, there's a picture on the internet that I like to show students at this time. If you don't mind me goofing around, I know I'm going on about a basic concept like pressure, but that's the sort of thing that I like to do. I like to make sure we understand these fundamentals before we get into some wacky nuclear physics. So let me share my screen one more time. And let's go to Google here and type tire pressure label. And we'll go to images. There's an image I like here. There's this, hold on, I gotta minimize our class here so I can find. There's a picture of a car tire. Actually, I think I saved this thing because I got sick of
digging for it.
Say that?
You got tired of digging for it, so you just kind of...
Yeah, I eventually actually did the smart thing. The problem is, where did I put it? Because that was many many moons and many cups of whiskey ago that I did such a thing. Hold on, I think if I know myself, I would have put it in the S drive, and I would have put it. Get out of my way, stupid Zoom thing. I would have put it inside the 10.
Click on the How to Survive College because I'm really not sure.
Wait. Oh, did you see that? Yeah. So I actually did a lecture once for incoming students. The CCRI convinced me to do a lecture on sort of just like the basics of college. And I thought it wasn't a bad idea because if you're a student coming in from high school, you may not understand that the rules are a little bit different. And actually that slideshow is really funny. There's like some funny images of like, hey, don't be a jerk and try to make friends with your professors. If you guys want some time, I can give you my presentation on how to survive college. I know you were joking,
Right.
but there might be something to
I was
that.
only half joking.
Oh, okay. Well, maybe I'll give you half the presentation then. Okay. So, wait. So hold on a second. Oh, here it is. Look, I'm so smart. Here we go. Okay. Can you guys see my screen okay right now?
Yeah.
Yeah.
All right. So let's look at a standard tire and this pressure label. It's telling us that the maximum pressure is 300 kPa, 300 kilopascals, or 44 psi. So how many times greater than atmospheric pressure is this tire inflated to?
3 times.
3 times, right? I believe that in the imperial system, it's 14.5 pounds per square inch is standard air pressure at sea level. Now, here's a weird, funny fact about air pressure in tires that might surprise you. I'm kind of I'm not like a mega cyclist, like I don't wear Speedos and stuff, but I have an old jalopy bike and I love riding it around, and sometimes I take it down to Colt State Park. I love riding my bike, okay? I think bikes are like the superior form of transportation. And if you look at the pressure label on a bike tire, when I'm filling up the air in my bike tire, which I saw a picture of just a moment ago, bike tires can be inflated up to 80 psi. Or sometimes even 90 psi. And that seems kind of weird to me. I mean, a bike is supporting way less weight than a car is, and yet the air pressure in a bike tire can be twice as much. Anyone know why that is? Why do bike tires get inflated to almost twice the pressure? I was hoping
Because the surface area is so much less.
Exactly. It's force per unit area. And wait, are you guys still seeing my screen?
Yeah.
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 I want to open. Why can't I? Yeah. Look, you can see. All right, this picture is kind of crappy, but it
70
says
psi.
76 or 70 psi.
Yeah.
Right. So okay, so you guys already understand my point. Then I'm yapping on too long here about this, but bike tires
Hello?
have way less surface area in contact with the road. So, I'm sorry, Riker?
I don't know. Ralph's freaking out.
Oh.
Yeah, what's good with you, Rav? Okay, Professor, continue. I'm sorry for Rav's
He's got
words.
tissue paper in his nose, man. That says it all. Really. Oh no! Now he's hiding his screen. See, look at you. Now he's muting his video.
It's not like Brittany. I'm very sad.
Raph, we like you, TP and nose and all. Okay, we're I'm totally.
Well, I mean, we didn't say that.
All right, guys. Before we ruin our whole day just talking about units of pressure, I just want to give you a couple of others that you're going to hear me use from time to time. Other units of pressure that come up in a science context. I particularly, astronomers love atmospheres. One planetary atmosphere is roughly about 100 kilopascals. Another unit of pressure that meteorologists like to use is the bar. And 1 bar is almost, but not quite, 1 bar is almost the same as 1 atmosphere. I've heard that some scientists wanted to phase the unit atmospheres out of teaching modes because they found it unhelpful. But planetary scientists love to measure pressure in atmospheres. You know, like Venus's surface pressure, the atmosphere on Venus is like 700 atmospheres of pressure. The pressure on Venus is so much greater than the air pressure on Earth that if you were to try to stand up on the planet Venus, despite it having the same gravity as Earth, the pressure of the atmosphere on top of your head would probably crush your ass like a tin can. You would feel the weight of like 10 dump trucks or something pressing down just from gas pressure. We don't think of gas as having any weight to it, but it does. And actually, humans are extremely intolerant to changes in pressure. As Rap knows, he's got the tissue paper up his nose. If you take an airplane up to cruising altitude, your ears pop and you feel a whole bunch of funny things going on. Okay, so now that you know about thermal pressure, you're better able to sort of go there with me and understand how important this concept of hydrostatic equilibrium is. Why do I care so much about hydrostatic equilibrium? Because hydrostatic equilibrium is part of the way that the sun regulates its internal energy. Hold on a second, I'm doing this badly. Function F5, what was it, slide 15? I can't even remember now. Okay, here we go. This balance between gas pressure and the self-gravity of a star is important because the star comes into a sort of self-regulating cycle here. Now, hydrostatic equilibrium, they never tell you this in Astronomy 101 class, but it's hiding a little secret, which is that the sun could not maintain hydrostatic equilibrium just by itself, were it not for the fact that there's a little nuclear bomb going off, a little nuclear reaction happening in the center of the star. And that becomes evident if you sort of explore what would a star be like if it didn't have nuclear fusion in its core. Believe it or not, you can make a star of gas that shines light just by squeezing a ball of gas down in space. And such a structure is called a protostar. And now let's go along with me here. Before, people have been thinking about the sun much longer than they've known about nuclear fusion, right? Nuclear fusion wasn't even a concept until Albert Einstein came up with E = mc squared in like 1905 or something. But scientists knew about energy in the 1800s. They were trying to understand, how does the sun maintain such an amazing energy output over time? And one of the ways that this becomes an interesting question, if you allow me to jump to a share screen mode here, pardon me, is just consider something like a fern fossil. You can dig through the layers of Earth and you can find fossils of ferns in rocks from hundreds of millions of years ago. And biologists will tell us that, you know, okay, maybe the fern of 100 million years ago. Can you guys see the fern fossil that I have here?
Yeah.
Yep.
Yep.
Although
Yeah.
it's not the same as the, you know, as the modern fern, they have a quite similar design and the size of their leaves have a similar structure. And a biologist will tell you, look, if this fern was sitting around on Earth, you know, 100 million years ago, and the leaves were about the same size as a modern fern, this fern has energy requirements from the sun, and this suggests to us that the light output of the sun was the same 100 million years ago as it was today. And if you keep extrapolating back, you start to find other pieces of evidence that suggest the sun's been pumping out its luminosity of 4 × 10⁻26 watts for like the entire history of the solar system, which is, how old is our solar system? Do you guys know? What am I,
Like
10
12 billion years?
No,
Four.
that's the universe.
It's like 4 or 5, right?
5 billion
4 or
years
5.
is an approximate, it's a one sig big answer, yeah. So if these ferns and other such pieces of evidence are suggesting to us that the sun's maintained a fixed energy output of 4 × 10⁻26 watts for like 5 billion years, how the hell does it do that? And people were asking this question before they even knew about nuclear fusion. So let's start by getting one piece of business right out of the way. And I actually want to take notes about this, if you guys don't mind. I'll keep that slide handy. Let's do a little set of notes on energy methods of the sun, because this is an important logical argument to work your brain through. Okay, so here we go. Energy of the sun. The first thing I want to say is that the sun is not a ball of fire. And this is important to mention Because if you go back in time and you read poetry about the sun, oh, Raf's got his helmet on now. Okay.
Yeah.
Safety
We're
first.
on the short
Safety
bus
first.
these days.
Yeah, it's dangerous work here, video conferencing. If you go back in time and you read, Homer and other ancient poets, they might talk of Ra or Helios riding across the sky in its fiery chariot. You know how it is
Apollo
listening
is
to
who you're
poets.
thinking of.
Poets
Yeah,
are
they were
full of all
They were
kinds of
just high. They were just
No,
super
it's your
high
last.
back in the day.
Where's my mute button? Okay, there you go.
Who we muted?
All right. It's pretty cool. I can mute you guys and I can unmute you too, I guess. All right, anyways, let's mute. Thanks, Raf. If you listen to poets, which is always a dangerous thing to do, they will give you the impression that the sun is a fiery ball moving across the sky. But here's why the sun can't be a ball of fire. That's because fire is a chemical reaction. And chemical reactions use up their energy rather quickly. Let's take a look at this picture here to learn some sort of basic science together. In the following chemical reaction that you can see on my screen, I'm going to mix a few molecules together. Let's say that the two red pellets are diatomic oxygen, which is part of the air that we breathe. So we have 2 parts of diatomic oxygen. And this guy over here looks like a methane molecule. The black atom is a carbon, and there's 1, 2, 3, 4 hydrogens stuck to it. If I mix oxygen and methane in a 2-to-1 ratio, a violent chemical reaction takes place, which is exothermic and releases energy in the form of light. You call that fire, by the way. And then the atoms kind of change up their dance partners, and the hydrogens jump ship from the carbon and attach themselves to oxygen, making, what is this here? What's this?
Water.
Yeah, that's water, H2O, right? How about what about this one, Riker? Do you know what carbon and 2 oxygens are?
Carbon dioxide.
Carbon dioxide. So in a chemical reaction, the atoms, the molecules are rearranged. The molecules on the input side are not the same as the molecules on the output side, but the atoms themselves have not been mutated. Hydrogen on the left is still hydrogen on the right. This is the difference between chemistry and nuclear physics. Chemistry just changes the molecules. Nuclear physics is going to change the atoms themselves. Anyways, let's suppose that you could make yourself a star that was a big ball of fire like Homer or Ovid would suggest. If you took a giant ball and you made it sort of the size or the mass of the sun, and you filled this thing up with oxygen and methane, and you just let it go to town, but if you required that the energy that the sun pumps out is the same as the energy it pumps out today, of 4 times 10 to the 26 watts, okay, then you would discover that the sun would burn through all of its chemical energy in a time scale of about 10,000 years. And by the way, this is going to be one of our homework problems today. Remember, we're doing homework at the end of our lecture today. Now, 10,000 year lifespan for the solar system, that may be good for some textbooks out there, wink, wink, but it's certainly not enough time to account for the age of fossilized ferns, dinosaur bones, and other sight lines of evidence like the radioactive analysis of moon rocks tells us that the sun has been pumping out energy for billions of years. So the sun just couldn't be a ball of fire because it would burn itself out too fast. And guess what? The old 18th century scientists, they knew this was true, and it freaked them out because they realized there's no way the sun is a ball of fire. It can't be. Believe it or not, there's another way the sun can draw energy as well. Students, I'm about to erase here. I notice Anakin and some taking notes. Can I erase, or do you need a second?
I'm good.
Okay. All right, I'm erasing then. Let's try another scenario. Believe it or not, you can make a star. Well, it's not exactly a star, but it's like a star. You can make something that looks, for all intents and purposes, like a star just by gravitationally squeezing a ball of gas. And now it's time to discuss something called gravitational contraction. Now, at some point, if our class goes according to plan, we are going to want to talk about protostars and how the sun formed. You can squeeze gas and you can heat it up, and the heating up of gas causes light to be emitted. In other words, take a star, take a ball of gas, contract it by even just a few meters, and the compression of that gas, you'll make a slightly smaller star. That star will become very hot. And as you know, when a dense object becomes hot, it will begin to shine light. It will be hot, compressed gas, and the gas can get so dense that the star will actually begin to shine like a black body. Class, what's a black body? I need to know that you remember this fancy term from our lecture on light. Does anyone remember what the heck a black body is?
The challenge is their colors due to temperature.
Thank you, Bella. Absolutely. It's an object. A black body means this. A black body means
I glow because I'm hot.
That's it. I glow because I'm hot.
It also emits radiation, correct?
Pardon?
It also emits radiation, basically, right?
Well, we have to have a talk about radiation. If you say radiation to an astronomer, they think you're talking about light, electromagnetic radiation. There's also particle radiation, which is, if you talk to your doctor about radiation, they think you're talking about alpha, beta, gamma rays, the ones first discovered by Madame Curie. In fact, I need to have a whole slide about radiation. So, Sal, that sounded like Sal, right? Sal, were you talking like particle radiation, or were you talking about electromagnetic radiation?
Electromagnetic.
Yes. Okay. Then we're on the same page. Black bodies emit radiation. They radiate. That's what they do. That's the glow part. I glow because I'm hot. And that means it's basically a hot, dense, glowy thing, right? Now, if you took a ball with the mass of the sun and you compressed it down due to gravity, which honestly, that must have happened at some point for our solar system to form.
I was gonna say, due to the gravitational contraction, because the gravity is squeezing gas and it's heating up so much, that's what's causing the pressure, which is keeping it in equilibrium.
Riker, this is my point as well, but there's one twist to this, Riker.
Yeah.
You can do a basic calculation in a slightly more advanced astronomy class, showing you the sort of the free fall time for a gas to collapse and how much energy it can give out. And it's a little bit over our pay grade because it would take about 45 minutes to do it. We don't want to get sucked into this. Right. But the answer turns out to be this. If you take a ball with the mass of the sun and you squeeze it so that it pumps out 4 times 10 to the 26 watts, that ball will have a total lifetime of 100 million years. In other words, the sun could support its current energy output for 100 million years just by squeezing and shining and staying in hydrostatic equilibrium that way. Now, 100 million years is starting to sound a little more reasonable for our, well, actually, it's really not reasonable because we know that the sun is billions of years old. We know our solar system and our Earth is billions of years old. If you study the stratified rock layers of Earth, any geologist can tell you, go ahead and look at the stratified layers of rock in the Grand Canyon, and they estimate that one of those stratified layers of rock will form in about 100 million years. The Earth is clearly older than 100 million years, suggesting that the sun is also older than 100 million years. And this is the whole reason I brought this entire argument up. Hydrostatic equilibrium cannot be the entire story of a star, because if it was, Riker's description would be perfectly accurate. It would be a star assembles itself due to gravity, it squeezes the gas gets hot, the star starts to shine, end of story. But the end of story actually comes 100 million years later when the sun has shined away all of its gravitational energy. What the hell would happen to the star then? it would grow dark, it would stop shining light, and gravity would suddenly start to take over again and begin to squeeze the star down further and further and further.
And that's what creates a black hole?
If it wasn't for the third effect, yes, it would eventually. What would stop gravity? Nothing. But it turns out that there is something that stops gravity, and that's the central temperature of your star starts to go so fucking berserk that it becomes hot enough for nuclear fusion to turn on. And this is how the sun has maintained a constant energy output for so many billions of years and will continue to do for billions of years to come. You guys see in my slideshow?
Yeah. It sounds like a
about nuclear fusion. And this is what I hope to get to in our lecture today. This picture that you see here is a picture of what we are going to call the proton-proton chain. It's a nuclear fusion reaction that produces energy inside the star. And I got to say, getting to talk to you guys a little bit about nuclear physics is one of my favorite parts of this course. So it'll be nice for us to tiptoe our way through these different reactions. I want to save it for last because once you start getting me going on nuclear reactions, oh my gosh, it's going to be hard to get me to shut up. So I also have a fun demo involving some radioactive uranium that I'd like to show you right here from my apartment. Okay, so we want to
still own
that? Dude, I am never giving that up. The feds are going to have to pry that from my cold, dead hands.
You keep it in your desk. It's right at like a very important level. Why?
I have a question. So like a light bulb has heat and gas inside it, right? And it emits
hold on, wait, no, Raph, I got to correct you there. A light bulb is a filament of wire that's glowing, and that glass is a kind of low pressure vacuum. The whole purpose of that glass bubble is to have a partial vacuum so that the air doesn't get heated up by the filament.
Okay.
Okay, well, it depends on what type of light bulb you're talking about.
Because I know there's light bulbs with gas in it, right?
Okay, fine, you're right. I was thinking of an incandescent bulb. If you're talking about a fluorescent gas tube like the ones at CCRI, yes, they are filled with mercury gas or something.
Yeah.
Wait, I think I lost your point, or you lost my point. What happened there? What was your point?
So like my point is that like what you're saying, it sounded like the sun was like a big, long-lasting like light bulb from what I understood from that kind of.
In some ways, the sun is a big light bulb, right? It's the primary light bulb that Cro-Magnon man had to work with until they figured out electricity, right? So
yeah.
So you're not wrong when you say that. The difference between a fluorescent light bulb and the sun is that the sun is a much denser gas.
Yeah, okay.
In fact, before we do the layers of the sun, let's just have a talk about the spectrum of the sun. Do you guys remember these things? Do you remember when we did this in our class?
Yeah.
So this is called a spectroscope, right? And the spectroscope uses a diffraction grating seen here to break apart light into its component wavelengths to make a spectrum. And what are the three types of spectrums that Dr. Kirchhoff told us?
Roy G. Biv.
Well, that's the visible. Roy G. Biv is the visible spectrum, but what are the three basic types of spectrum?
Gamma. It wasn't like gamma rays.
No. Those are regimes of the electromagnetic spectrum. I'm talking about types of spectrum. Maybe we need to go back to that slideshow. Spectral type. What types of spectrum found in nature? Does anyone know what the shit I'm talking about here?
I have no idea.
No.
Okay, that's that. Then we got to go back to school. Back to old school.
Yeah.
What's this picture all about?
This year is because of Corona.
Hey, who's Chatty Cathy in the background there? Mute yourself. Oh, sorry. Sorry, Sal. I'm sorry. I'm trying to have fun with you guys. Guys, what's this picture all about? Please tell me this picture means something to you.
Is it electromagnetic spectrum?
Well, all of these are part of the electromagnetic spectrum, but there's a difference. What does spectrum mean?
That's the
like a ray.
Sorry?
Of things? A range of things?
Well, okay, in a general
Like
sense.
from one place to another?
Look.
I know there's.
All right.
Are you talking about
No.
continuous spectrum, emission line spectrum, and absorption spectrum?
Who said that?
Hope.
Oh, Hope. Thank you. Me and Hope are talking now, okay? The rest of you guys just write down.
I'll mute myself.
Let's talk about the spectrum of the sun, okay? In a weird way, the spectrum of the sun is actually all three types of Kirchhoff spectrum at once. The sun, let's look at it. It's a ball of gas, right? And it's got a hot, dense interior. What type of light does a hot, dense, I don't want to say solid because there is no part of the sun that's in the solid phase, but this is why Kirchhoff, he could have done better in his description of Kirchhoff's laws. Instead of saying a hot, dense solid, he should have said a hot, dense thingy. I've got a demo in mind. Don't move.
What's that last thing say? A hot, dense texture.
A hot, dense interior. Sorry.
Okay.
Hey, Hope, where are you?
Yeah.
Hope? You're right there.
Yep.
According to Kirchhoff's laws, what type of spectrum should this flame be producing?
Emission line?
And what's the definition of how emission line spectrum is produced?
A hot, thin gas produces an emission line spectrum.
Exactly. So it looks like we're understanding Kirchhoff correctly here. It's a hot gas and it's glowing, right? All right. Now it's time to learn something. This is a very instructive demo for me at some point. Screen share, iPhone. Jordan, I might need your help. If you could be my classroom assistant for just a second. Okay. If you don't mind, can you, my friend Jordan is going to hold this lighter here, and don't keep your hand away from the metal or it'll get hot, but flick that flame, and I'm going to hold the spectroscope up here. Okay. Do it against the background. Yeah, that right there. Okay, so flick it. Okay, let's see if we can put this into our, oh, hold on. For the purpose of video, I need to move this over here. All right, so another dangerous demo done in Professor Britton's apartment here. Let's go to our spectroscope. Hold on, I need to zoom in a bit.
Safety first.
Just let me know and drop it. Oop, here we go.
Ooh, it's all right. It's all right right there.
It's a.
Yeah, it's hard to get. What type of spectrum does that look like?
Continuous.
Oh, right there. Oh.
Continuous.
Yeah, thanks, Jordan. Have I made my point?
Yes.
What's my point? What's my point?
It's the one you made.
Riker, I can't see your shining face.
Yeah, I don't know why it like disconnected my camera for whatever reason. I'm trying to get my video going, but it's not.
Well, at least we can hear you. Riker, what kind of spectrum was that?
That was a continuous spectrum.
But Hope told me it was going to be emission line.
She lied.
She did. Well, honestly, in Hope's defense, the first time I ever looked at the spectrum of a flame, I thought I was going to see an emission line as well, because Kirchhoff told me that hot, dense solids produce continuous rainbows.
Oh, I know what you're saying. Is it like there's gases inside the sun? So like, do those gases produce those spectrums?
Kind of, but hold on. You would think that air was a thin gas. Look, I can push my hand through it. I don't get a lot of resistance. You would think that if you heat up air, it would produce an emission line spectrum, the emission line of oxygen and nitrogen, which is air. But it doesn't.
Absorption.
Fire produces a continuous spectrum. And the point that I'm trying to make is this. The air in this room, this empty box of nothing, or almost nothing, is still too dense to produce an emission line spectrum. Air is not a thin gas. Air is a thick gas that is so thick that if you heat it up, it radiates like a black body. The spectrum of heated up air is the same as the spectrum of a heated up brick of iron. You see what I mean?
Yeah, because it's like if you put your hand on a hot brick of iron, it's equivalent to putting your hand in a box filled with hot air that's as much as that iron, right?
Well, hold on, Raph. That's about heat transfer. No. If you touch a hot brick of iron, it will burn you much worse than a. I'm sorry, Raph. But that's
No,
not
like
true.
if it was at the same temperature, if the
Oh, no. But the problem is you said touch it. That's where you went wrong, is when you said touch it. I'm talking about the light that it gives off. Okay?
Oh, okay.
In other words, the interior of the sun is a hot, dense thingy, and it produces black body light. It produces a rainbow. Now, the outer layers of the sun are lower density gas. Now, they're not cool, but they're a cooler, thinner gas. Believe it or not, even the density of gas at the surface of the sun is still thick enough to produce black body light. And what makes it more—
Isn't that the photosphere?
The sun has an outer exterior wispy layer called the corona.
Virus.
I've heard enough about corona.
You said corona. It's not
Virus.
Well, I'm sorry?
I've heard enough about coronas. Thank you.
Oh, yeah. Well, you're going to hear a little more about coronas before this day is done, so hang on to your hat. Look.
It's giving me PTSD.
You can actually get— by the way, they named the coronavirus after the corona of the sun, so we were here first, okay?
It wasn't the beer?
The beer was also named after the real corona. Anyways, the point I'm trying to make is you can get all three types of Kirchhoff spectrums from the sun. The sun is like a black body. The sun also shines black body light through cooler gas, giving you an absorption spectrum. You can also get emission lines from the hot, thin gas that does surround the sun in the corona. Okay, so when I put my spectroscope up to the sun, what type of spectrum does the sun produce then? Overall, which wins out? What is the spectrum of the sun? Is it emission line, is it black body, or is it absorption?
Absorption.
Absorption.
Absorption is correct.
Absorption.
Let's go ahead and let's look at, although I can hold my spectroscope up to the sunlight, it's much nicer to go to, Boston University has a very nice heliostat, and let's go here to the internet and let's take a look at BU spectrum of the sun. If you hold a high resolution spectrograph up to the sun, this is what you are going to see. If you break the sun's light down into its component wavelengths, let's open up this image here. This is what the spectrum of the sun looks like. Now listen, students, this is a very important point I'm gonna make, and this matters for our entire class. Even those people who took 1010 need to perk up their ears now, because we're moving quickly towards talking about stars in general. The spectrum of the sun and the spectrum of all stars is an absorption line spectrum. You see that? Look inside the spectrum of the sun and you see something that's like a black body. It's a continuous rainbow, but it's fractured by all of these dark absorption lines. Where are these absorption lines being produced, students?
From the stars and the suns, you said?
Well, what do you mean by the stars and the suns? That don't make no sense to me.
Like they're the reasons why. Those are the reasons why those black lines are there. That's what I thought you said.
We're going to have to take a quick peek at Cecilia Payne-Gaspachin's 1925 PhD thesis, considered a gold standard for PhD theses in astronomy. Hold on a second here. Slide 52. I'm going to tell you a story about Edward Pickering later on, but this woman was one of the early pioneers of women in astronomy, Cecilia Payne-Gaspachin's 1925 PhD thesis, quote, "Stellar Atmospheres, a contribution to the observational study of high temperature in the reversing layers of stars." Say what? Okay, her wisdom and her genius was to realize that these absorption lines were being created in the photosphere of the sun. That you have a hot, dense interior in the lower layers of the photosphere, and they produce a perfect white blackbody rainbow light. But as they pass through the thinner, cooler layers of the photosphere, individual atoms are absorbing unique wavelengths of energy, resulting in the absorption line spectrum of the sun. This is my point. The sun's spectrum is an absorption line spectrum, and these absorption lines are telling us what atoms are in the bloody photosphere, the surface layer of the sun. This is how we know what the compositions of all stars are. We know that most stars have a similar composition to our sun. Now, if you've been listening to me, there's a message, and let's write it down.
Is it all the same for like supergiants as well?
Supergiants also produce absorption spectrum. Now, supergiants are much different than the sun, and you'll see why they're different with time. But for now, you've got to learn something important. All stars produce absorption line spectra when you look at their spectrum. The sun produces an absorption line spectrum. I don't know. In fact, I don't know if I showed you this, but you know, looking at that cartoon looking at the little absorption lines, honestly, looking at a spectrum like this is for little kids. This is what you show your baby astronomy students. You show them a little cute rainbow, some dark lines, and you say, how cute is that? But if you're a badass, when you look at the spectrum of the sun, you scan along this with a computer program, and you measure the intensity of sunlight, the brightness of sunlight as a function of wavelength. And then what you do is you produce what's called a blackbody profile spectrum. And I have one that I'd like to show you. This is kind of for people who've got their thinking caps on, okay? So this isn't just for everybody.
Yeah.
Okay, so yeah, Raph, you got the tissue paper in your nose. You're ready to go, okay? So over here, this, I know, people love looking at plots. This is a graph of the sun spectrum shown in black. So let's look at what we're plotting here on our different axes. I need to move this out of the way. On the y-axis, we have the intensity of sunlight, the brightness in watts per square meter.
I'm not seeing that graph.
On the x-axis, we're plotting wavelength in nanometers. Where does visible light fall on this scale, students?
I don't know. I'm not seeing that graph.
Yeah, Professor, the graph is not on the screen.
There's nothing there.
Oh, that's what you guys were trying to tell me. All right, let me see what are you seeing right now?
You.
You.
What a letdown. Okay, hold on. Let's try this again. I know. Share screen. What are you seeing now?
Now I'm seeing it.
Yeah.
Wait, how about now?
Now it's the
Yeah,
graph.
I'm back to the graph now.
All right.
Sun spectrum versus thermal radiator.
Thank you. I'm sorry. I don't know what happened there. Okay. Let's look at this again. Can you see my mouse as my mouse moves around?
Yep.
Yeah.
Okay. On the y-axis, we are plotting the intensity of sunlight or the brightness of sunlight in watts per square meter. On the x-axis, we're plotting wavelength. Wavelength in nanometers. Where is visible light on this spectrum, students?
4 to 700.
400 to 700. So this is what your eyes are sensitive to. Oh, who's doing
Wait,
that?
that's on your screen?
Yeah, that came up. Michael, erase that.
Yeah. Okay.
You're changing the spectrum of the sun.
How the hell do we do that?
There is a way to do that, but I don't want to tell you now.
I won't tell anyone. No one will ever know. Wait, that's not me. That's not me. That's not me. Who's doing that?
Michael.
Sorry, that was me. That was me. I'm a terrible professional.
I figured out how to do
Don't start blaming me.
All right, hold on.
I saw someone raise my name. I was just like, that's not me.
All right, no, that was me. I was being a bad person.
That's not
Okay.
me.
All right, wait. All right, now we're done. Right, we're done.
That was me. I tried to. I like saw it and I was like, wait, is this how you do
I
it?
guess this is a collaborative graph here. Okay.
Okay.
All right. Okay, hold on, guys.
Sorry.
Now the real spectrum of the sun is shown in black. Okay. And in green, they're showing you an idealized black body. Okay. I've got an eraser tool.
Sorry.
All right, that's okay. That's okay.
Couldn't resist.
So the idealized black body is shown in green, and the real spectrum of the sun is shown in black. And there's a couple of different points to this slide here. The first is that, to a first approximation, the spectrum of the sun has super, super good agreement with an idealized black body at 5800 Kelvin. So basically, the sun is like, a star is kind of like the closest thing to an idealized black body that one can get in nature. But the sun does deviate from an ideal black body. Do you guys see all these little dips here where the intensity of the sun drops down? Those are actually absorption lines. Those dark lines that you saw in the picture when I show you the rainbow with the dark lines, here the absorption lines are small dips in the intensity of the sunlight. And astronomers go insane mining information from these dark absorption lines. Professional astronomers spend most of their time making plots that look like that and then diving into these absorption lines to study aspects of a star's radiation. So here's a picture from a professional spectrum, function F554. Are you guys seeing this?
Yep.
Yep.
Here's our hydrogen alpha here at 65, 63 angstroms. Astronomers actually go in with computer programs and they model these dark absorption lines. And you can not only find out what element is causing the absorption line, whether it's hydrogen or sodium or iron, but you can even model the shape and learn things like the conditions of a star's temperature and its pressure, its magnetic field. You can study the rotation of a star. There is so much freaking information you can get from light. And thank goodness, because all we have to work with in our cosmos are photons. You can't take your Millennium Falcon to the Andromeda Galaxy. Not yet, goddammit. And I'm mad that I was born in such a time where I can't do this thing. But until then, until
we can't, doesn't mean they can't.
Well, someone can. But in the meantime, all we can study are these photons, and that's how we get to learn about outer space. That's how we do it. Okay, so here's what I want to do. I have no idea how I'm doing on time right now because I got lost.
We're over by a minute.
Yeah, we're over.
Oh,
You're good on time.
I didn't even get to the nuclear fusion. Okay, you know what? I guess we had fun. I didn't mean to spend quite so much time talking about the spectrum of the sun, but I did that. Oh, wow, we're so screwed. Okay.
Wow, thanks.
All right, no, okay. Fine. I'm not
very
gonna
reassuring.
I'm not going to go over lecture. What we're going to have to do is we're going to have to continue on lecturing about the sun next time. That's not what I intended to do, but I think that's just, I kind of got a little too intense about the spectrum of the sun. I wasted some time there. Okay, so fine. Our next job students, let me go to gallery view. I'll give you guys a little pause in the action, and then we're going to do our homework together, and that's the second piece of business we need to do today, correct?
Yeah.
Did everyone submit their labs?
Yeah.
Yes, I did
not.
submit mine.
All right, Tim, because Tim didn't have the code to log in with us. Tim, and I want to tell everyone this too. Guys, I have, not only in Blackboard do I have the videos, but the videos are on YouTube as well. So I'm going to share my screen with you one more time. And anyone who wants, even if you can't access Blackboard, you guys can go to my YouTube page. Okay. Can you guys see this here?
Yep.
Yep.
Yeah.
Just go to look up Brendan Britton or something, or I can send you the link. And I have not only our first lecture on the sun here, but Tim, for you, this is our lab on the rotation of the sun, okay? So you can show this to your family and your friends.
Yeah, I saw it yesterday. I just haven't finished it yet.
So Tim, just get something done, and then you got to submit that. Okay.
Got it.
You can just kind of follow along with the argument. I know the video takes a while to get through, but just kind of skip ahead, get some stuff done, and just submit something to me. Okay.
All right.
Let's get the channel subs.
So we need to do our homework now, correct?
Yep.
And then we're going to submit that. So let's take a pause. I know you guys could use a little break. Let's start up again at 1 o'clock, and we will do our homework assignment. Unfortunately, you know what happened, guys? We were supposed to get into the interior of the sun and nuclear physics, and I talked too long. I wasn't paying attention to time. I got lost in the sauce. So there's a couple of questions about nuclear physics in the sun, and we're going to kind of describe it as we solve the problems. I think that's the best we can hope to do, okay? So there'll be a little bit of lecture squeeze in there, but we'll try to get through the homework. I'll try to make sure that it takes less than an hour to do it. That's my goal. So let's take a pause. I'm just going to mute myself, and we can rejoin the crew at a little after 1 o'clock, okay?
All right.
All right. Can you stop the screen share so we can go back to grid view?
Yeah, sorry, I didn't realize I was still on that view. Okay, so I'm just going to mute, and I'll see you guys a little after 1 o'clock, okay? I'm just going to take a 10-minute pause.
So basically, everything I said is on YouTube. All right, next time I'm gonna have no face.
No. This is part of the fun. No one looks at my YouTube page. I'm not an
Nah, I'm gonna give you a shout out. You're about to be famous.
Oh shit!
No, everyone's gonna be like, "Oh, who's that Asian kid with the?"
Don't blow up my game, Ramos.
Let's get to 100 subs.
You're about to be
You
famous.
guys know that you can give yourself a background?
Yeah, you can give yourself a background. There's one. You can download a package of nebulae, and it's pretty cool. One of the kids in the other class, his background is a Pikachu. Can you guys see this?
Yeah.
Am I like
the Northern Lights?
Aurora Borealis.
Why do I not?
It's cool if you have a solid color. Yeah, look at this. I feel like this is like some Twin Peaks shit right here.
What program is that?
Oh, you just go into some video settings and then go to the tab called virtual background, and you can give yourself a virtual background like this.
I don't even have settings.
Whoa. Hey.
Dude, can I show you guys something? Wait, really quick. I want to share my screen. Can I show you guys something fun? One of the students in my other class, can I show you how badass he is? Look at this other lecture here. And I want to show you his background. He's got a Pikachu. He's like, his background, I don't know how he did this, but Thomas like turned his background into a bloody Pikachu. Come on, internet. Hello?
Oh, I can also touch up my appearance so I don't look ugly.
What the heck?
Can you guys see that?
Yeah.
Thomas's background is a Pikachu. It makes the video so much fun. Every time I look at him, I'm like, what the hell? This is awesome. Hey Ramos, I like your glowing lights there. That's a pretty cool backdrop.
Oh yeah, my LED lights. I got them like the other day. They're pretty nice.
Nice.
Were they expensive? I want to get some. I mean, I have some for $5.
I'm getting a drink of water. I'll be back at 1.
My LEDs lights for like $10.
I got it. These were 30. And like
So
they
this
go
is
like around.
this is
like,
touch-ups that make me look less ugly.
Oh my God, Michael, how did you get to the Golden Gate Bridge so fast?
Oh, I think it's crazy. It's not.
Yo,
I
Raph.
just, you know.
Yo, Raph, you still bleeding?
Nah, not right now. I hope because I have work later, and I heard that heat makes you bleed more. So like, I'm not trying to, because I'm on grill. I work on grill at Chipotle. So like, yeah.
Which Chipotle do you work
Essential
at?
employee.
The one next to CC.
No way. For real?
Yeah. It's mad easy.
I go there. I go there all the time, like after like baseball practice or something, or like after a game. Me and my teammates will just go over there. I've never seen you.
Look, I'm in our astronomy class.
Yeah, I don't know. But yo, check this out. I do this.
Yo, he's at school, boy.
I'm in our astronomy class.
This kid's in school.
This kid's insane, dude.
Wait, who's at school?
Look at Michael. He's at school right now.
Oh wow.
And I'm turning off my touch-up appearance because I just want to be real.
Hey guys, Vsauce, Michael here.
You said Vsauce? Oh my god.
You know who that is?
You guys are
Yeah, of course.
I'm
Who
like-
doesn't know what Vsauce is?
I
That's
don't know.
not funny.
I fucking love that guy.
Michael here, and then he like jumps into
Hey,
like the view.
wait. Hey guys, Vsauce, Michael.
This kid.
And he says some trippy shit like, which one's faster, the light or the dark?
Yeah, check
Anyway,
out my
I'm gonna
cool
see if I can
poster.
get the Vsauce music like pumping in the background. Hey guys, Vsauce, Michael here.
Yeah, I
What
got a nebulae.
is worse, 1,000 ants or 3 lions?
I have work at 4. You think this will probably be done before 4, huh?
Yeah,
you should be
I would
fine.
hope so.
I mean, I know they say specifically don't go out, but you know.
I mean, you're an essential employee.
Yeah, exactly.
Dude,
You know what
honestly,
Chipotle's
just
open.
go out. You know, do your thing. You know what I mean? Don't let this shit stop
Everyone's
you.
getting the coronavirus, but me and my boys are getting Bieber fever. You feel me? So it's not really like, I don't know. We're different. You know? You and me, we're different. We're different. So, like, I don't know.
Oh my god.